So for this session, what we want to do is talk a little bit about some of the general properties of telescopes. We're not going to go into too much detail in the many different kinds of designs that you can have for telescopes, but more look at the big picture of what are the goals of these telescopes and what are some of the main limitations. So when you think about a telescope, very often people think of, oh, I'm going to zoom in on something in the sky. But in general, the main purpose of a telescope is not to magnify images. Usually, telescopes will have a certain amount of magnification, but that's not usually the key goal. When I have an object that's very, very distant, then the light that it's giving off is going to be spread over a much larger region before it actually gets to me. The further away a light source is, the dimmer it appears to be. So very distant light sources, distant light sources appear very dim. So if all you were doing was just zooming in on that image, you'd zoom in, you could potentially zoom in so much that every little bit of your image is barely getting any light at all. You'd basically zoom in until the image is completely invisible. So what you need to do is to do two things. You need to collect more light and get a very high angular resolution to be able to see very, very small details. Think of it this way. Let's say it's raining and you need to collect some water. Well, if you just go outside in the rain and hold a water bottle out, it's not going to be very effective because the opening is not very large. Okay? In the same way, if we're trying to look at very, very distant images, or look at very, very distant objects where the light that's reaching us is very dim, if you go out there with your eye is not going to be able to pick up very much light. However, let's go back to the rain analogy. If I wanted to collect water in that bottle, I could use a funnel. If there's a large funnel over top of the water bottle, it's collecting more of that rain. More of the rain that would have missed is now being funneled into that bottle, and we collect more rain. In a very similar way, telescopes are basically acting like light funnels for our eye. Having a large telescope collecting lots and lots of light and getting that light to focus into our eye allows us to see these very, very dim objects. So in order to observe these objects, we need to collect more light. So telescopes collect light. So basically, the larger the telescope, the larger the what's called the collecting area of the telescope is, the better. Now, this is not the only thing that we want to do to make the telescope better, because another aspect is the angular resolution. So when we talk about angular resolution, it's basically the smallest angular size on the sky that two objects can be apart, and I can still distinguish them as two individual points of light. Think about this. Think about driving down a road at night, a highway at night, where very, very far off in the distance, you see the headlights of a car. But if that car is far enough away, those two headlights, if that's far enough away, it's basically going to get so close together, such a small angular separation, that it's going to just look like one headlight. If there's a little bit of blurriness to it, it's going to look like one headlight. And it's not until that source gets closer that you actually can resolve that with your own eyes into, oh, there are two headlights there. So if I'm trying to see a small detail on the sky, I want my telescope to have a very good angular resolution to be able to discern those really, really small details. And again, increasing the size of the telescope both collects more light, and for reasons that we're not going to go into, larger telescopes also have this better angular resolution. So large telescopes have collect more light, and have better resolution. And again, these are two of the key properties that determine how good a telescope actually is. If you want to see something that's very far away, it's probably going to be pretty dim, so you have to collect a lot of light for that. So, for example, the human pupil has a collecting area of about 18 square centimeters. Not very much. If you just go outside at night, objects that are even somewhat far away, they're going to be too dim to see. Whereas a 3-inch telescope, the objective lens of that telescope, the primary lens of that telescope, is about 3 inches across and can gather about 256 times more light than the human eye can. And it funnels that light into the eyepiece, and that goes into your eye, so you can see much dimmer objects. But again, bigger is better for telescopes. The Gran Telescopo Carinaris in Spain has a 10.4 meter diameter mirror and gathers over 12 million times more light than the human eye does alone. In terms of angular resolution, the Hubble telescope, if you had a quarter, the Hubble telescope could identify the two sides of that quarter as being, two separate points of light at a distance of 99 miles away. And the Keck telescope in Hawaii would be able to resolve two sides of a quarter from 231 miles away. Again, the larger the telescope, all other things being equal, the larger the telescope, the better its angular resolution is going to be. Now, you've probably heard that we put telescopes into space. So, for example, the Hubble Space Telescope, or more recently, the James Webb Space Telescope. So, why do we do that? Well, it's not because we're putting these telescopes appreciably closer to the stars to be able to detect them. Again, the Hubble Space Telescope is just in, low to mid-Earth orbit. So if this is the Earth, it's just a tiny, tiny bit above that. It's like saying if I move from here to here, well, I'm closer to San Diego now. Kind of, but not in any practically useful way. So again, we don't put telescopes into space to put them closer to the stars. We do it for a couple of other reasons. We want to avoid, first, light pollution. So if you've ever tried stargazing in a city, it doesn't really work because there are too many other light sources that wash out the stars. If you want to get a very clear skies, you want to go to someplace isolated out in the field or on a mountain or something like that to avoid this light pollution. Putting it into space, even better. We want to avoid atmospheric turbulence. Earth's atmosphere is not perfectly smooth. It goes through little bits of turbulence. And just like when you look at the air over top of hot asphalt or over top of a barbecue, how you see that kind of little wavy line starting to show up and that little distortion start to happen. Earth's atmosphere does that all the time. And this causes the twinkling of the stars, but for astronomers, that's kind of annoying. It causes the images to blur, and we want to avoid that. Also, we want to study astronomy in all sorts of different parts of the electromagnetic spectrum. We don't just want to rely on visible light. We want to be able to look at other forms of light as well. The problem is Earth's atmosphere absorbs most of the infrared light and most of the ultraviolet light before that light actually makes it to the ground, and essentially absorbs all X-rays and gamma rays. So if I want to study the universe in X-rays or gamma rays, infrared or UV light, we basically have to put these telescopes into space so Earth's atmosphere doesn't just block out all those signals. Basically, from the Earth's surface, you can really only do astronomy by looking at visible light or radio waves, because radio waves can very easily move through Earth's atmosphere. So I just want to talk about a few technologies and a few aspects of these telescopes. I mentioned how the atmosphere causes this shimmering effect for stars. Again, similar to how the air over top of asphalt looks like on a hot day with that kind of shimmering effect. That happens in an effect called, this kind of atmospheric turbulence, and causes stars to twinkle and images from ground-based telescopes to become blurry. So basically, if I had 2-point sources of light, so let's say here and here, but as that light passes through the atmosphere, it makes that light all blurry. Well, those 2-point sources of light will basically look like one kind of blob. They're so blurry that we can't even distinguish that there's 2 points of light. However, there's been a technology that has developed over the past couple decades called adaptive optics. And this is a way for ground-based telescopes to kind of filter out the effects of the turbulence of the atmosphere, the distorting effects from the atmosphere. And I'm going to play a quick YouTube video to kind of show what's going on with this adaptive optic. And we've got the nice, cute little, end of that video. But I just want to kind of make mention of a couple of the technologies that were just described in there. So again, we use this high-powered laser to stimulate a layer of sodium atoms in the upper atmosphere using that same kind of absorption and emission effect that we were talking about with spectroscopy. They actually need to constantly monitor air traffic because you're firing high-powered lasers into the air, and if a pilot got one of those lasers in the eye, it would be instantly blinding, which we obviously don't want to do. And when that part of the sky starts to glow, a computer can literally cause one of the mirrors in the telescope to deform, like full Transformers style, into the right kind of corrective mirror for the atmospheric distortions at that point. And it does this on a fraction of a second by fraction of a second basis. So it's able to take these images that without the adaptive optics would be very blurry, not giving us very much information, and able to clarify those to a remarkable degree. This is a infrared image looking at the galactic center with adaptive optics off. And then when you turn it on, how much of an improvement you can actually get in the images of the stars in this part of the sky. Again, just some really, really cool technologies. We have to find some ways of either putting telescopes into space or canceling out the distorting effects of the atmosphere without just removing the atmosphere entirely. That could be another solution, but with everyone choking and dying, we'd probably get some reduction in grant funding. Anyways, some other aspects, as I mentioned, Earth's atmosphere blocks a lot of different parts of the electromagnetic spectrum. Most of the ultraviolet and infrared part of the spectrums, basically all of the X-ray and gamma ray parts of the spectrum. So since different parts of the spectrum highlight different kinds of physical processes, we really like to get all of that information. This is the same galaxy, looking at it in X-rays, ultraviolet, optical, near-infrared, mid-infrared, the radio continuum. This one's looking at the blue in here is looking at a specific spectral line of atomic hydrogen, molecular hydrogen. This one's looking at some of the spectral lines of carbon monoxide. And again, all of these different parts of the spectrum highlight different physical processes, different elements that are being detected in these sorts of things. And when we're designing telescopes, it takes different kinds of instrumentations to make a visible light telescope from a infrared telescope, from an X-ray telescope. All of these require different kinds of technologies, so we have to design these telescopes in very particular ways to meet various science goals. In radio astronomy, especially, this is used in some other types of astronomy, but radio astronomy especially, we said that the larger the telescope, the better the angular resolution, the smaller the details we're going to be able to see. Well, interferometry is a method where you can take multiple telescopes, and again, this is mostly done for radio telescopes. You can take multiple telescopes and network them together So they will act like a gigantic telescope with a size as large as how far those telescopes are set apart from each other. So this method is referred to as interferometry. And if you've ever seen one of these kinds of pictures of a whole bunch of satellite dishes kind of linked together, this is one of those interferometers. This is the Very Large Array in New Mexico that uses a set of smaller dishes to act like one gigantic dish. So we get very, very great angular resolution. There's a set here, and then there's a couple other telescopes listed even further away to get more and more of that angular resolution. And this is an image of the radio emissions from the center of our galaxy from the Very Large Array. At the very center of our galaxy, there seems to be this point where there's a huge amount of radio light coming from that. And since we have this interferometer, it gives us a good enough resolution to really see that in a lot of detail. And in this particular example, this very, very bright source of radio emissions is called Sagittarius A star, which is most likely the accretion disk around a supermassive black hole at the center of our galaxy. Again, later on in the course, when we talk about galaxies, we'll see that most large galaxies, like our own, have supermassive black holes near their centers. So a couple other things. I just wanted to mention a couple choice telescopes that are currently in operation and just kind of mention some of the comparisons between them. Hopefully, in the past couple of months, you've heard about the James Webb Space Telescope. It was launched last December and has started taking science data. I think they started taking science data around June. And this is a fantastic new telescope. So far, all of the deployment, all of the calibration for it has been remarkably successful. We're probably going to be talking about aspects of the James Webb Space Telescope for, decades. They think it's going to last a pretty long time, much longer than the original design was for, based on how well it got placed into its orbit. And the James Webb Space Telescope looks at a little bit of red light, but mostly infrared light, because it's one of its main design goals is to be able to look at galaxies that are very, very far away. And if they're very far away, we're seeing them as they were very, very far into the past. We're trying to look for some of the first galaxies and study their properties. But those very distant galaxies, their light has been very, very redshifted. So that's why it's using more of the infrared light and looking for that. As I mentioned, a lot of these other areas of the regions of the spectrum, we have to put satellites in orbit to make those measurements. So this is an artist's conception of the Chandra X-ray satellite, which has been operating since 1999. And again, looks at different parts of the electromagnetic spectrum, looking for different sorts of signals that tell us different things about those kinds of physical systems. This one is one that's near and dear to my heart. This is the Green Bank Telescope. This is a very, very large example of a radio telescope. This telescope is fully steerable, so this entire structure, which is over 100 meters across, the dish is 100 meters across, this entire thing can rotate around and aim to different parts in the sky to take radio images and radio scans of those different parts in the sky. And I've actually gotten to go to this site a couple of times on a tour. And just to kind of get the scale of this thing, let me zoom in a little bit more on this. Just to get the scale on this thing, there is a stairway that goes up, and you can see the sides of the stairways just kind of going back and forth up here. And going across this catwalk is not for people who don't like heights, because it's the catwalk, it's a kind of steel grating that you can see through, and then about 200 feet of nothing below you, just through that steel grate. And again, this is one of the largest radio telescopes, definitely the largest, I think the largest fully steerable one. There are other larger ones than this, but again, a very impressive scientific instrument. And this telescope, remember I said that we can link together multiple telescopes to basically act as one giant telescope. And this is one of the telescopes that was part of the Event Horizon Telescope, the Green Bank Telescope, VLBA, a bunch of other telescopes across the world. And these were all linked together in order to make a telescope that was essentially the size of the Earth, or at least had that kind of angular resolution. And using, again, this is not an easy thing to do, linking together these telescopes. It takes a tremendous amount of data, a lot of time to analyze your results by linking together all these telescopes. But this is the collaboration, this Event Horizon Telescope, this was the collaboration that used these linked telescopes to get us the first direct image of the region immediately around a black hole. So this is the first image of a supermassive black hole in another galaxy. I think it was M31. I will have to double check on which galaxy this was. I think it was M87, actually. So this is the shadow of the black hole. That light kind of gets bent around that to make this kind of shadow, and the event horizon would be just inside of there. Again, in order to get this resolution, we had to make a radio telescope that is literally the size of the Earth by linking together these other telescopes. I have heard people say, oh, isn't this really blurry for a first image? But this is actually probably the clearest image you've ever seen. The size of this, the angular resolution that we're talking about, would be like seeing a donut on the moon. And again, a huge amount of technology, effort, data analysis skills go into making something like this work. So again, this session, I just want to kind of talk a little bit about telescopes, how their goals for collecting light and increasing angular resolution, some of the reasons why we put telescopes into space, and just talk about some of the technology that goes into these amazing devices.